Hi, everybody. So today we're going to start a new chapter where we move into states of matter, and later on we'll be talking about gas laws. Before we go into our three states of matter that we'll be focusing on, I just want to remind us of what kinetic energy is. So kinetic energy is really just the energy of motion, and that's something that we want to keep in mind because as we look at these three states of matter, we want to remember that all of our matter is made up of tiny particles that are always in constant motion. And one way that we know this is scents can travel. So if a classmate is using hand sanitizer in the back of the classroom, eventually we'll end up smelling that in the front of the classroom, showing us that yes, scents can travel. So our first state of matter, and a lot of this will probably be a review for you, but I just want to touch on it really quickly so that we can refresh our minds. So our first state of matter is solids. Most of the solids that we look at are ionic compounds. And a few characteristics of our solid are that they're packed together. They're held together by strong forces, which means that they have really high melting points. It's going to take a lot of energy to break those forces. And they vibrate around in fixed points. They're incompressible, they have a definite shape, and a definite volume. A few vocab words that you might hear as we're going through this chapter are, when we're referring to solids, you might hear crystal. A crystal is just a solid with atoms, ions, or molecules arranged in a nice, orderly, repeating 3D pattern. Another vocab word that you might hear is allotrope. An allotrope is a molecular form of an element that exists in two or more different forms in the same physical state. So for example, graphite, charcoal, and diamond. There's a picture down here at the bottom of your screen that shows these substances that are all made out of carbon, but have very different shapes and looks. An amorphous solid is a lack of internal structure. These atoms are randomly arranged and they're not highly organized. Some examples of this could be glass, plastic, or rubber. So if we look at this example down here of an amorphous solid, we can see that we really don't have much structure. Again, the atoms are more so randomly arranged. For liquids, they're packed together almost as closely as they are in a solid, but they're held together by weaker attractive forces than a solid would be. The atoms are able to slide past each other, and a lot of our liquids are polar. They have positive and negative ends. For example, water. We talked a lot about that in our bonding chapter, how it had the partial negative and partial positive end. Liquids are nearly incompressible, they have an indefinite shape, and they have a definite volume. When we're thinking of our liquids, remember, like we mentioned a little bit ago, water was an example that had these strong intermolecular forces, these attractive forces between our molecules. So right here, we can see this yellow arrow is indicating that intermolecular force of the attraction that we'll have between an oxygen atom and a hydrogen atom. And those are what we call intermolecular forces. Last state of matter are gases, and our gas particles are very far apart. If we're looking at a sample of gases, it's 99% empty space. Most are nonpolar molecular compounds, meaning they don't really have an attraction for each other. And we're not going to see any of these attractive forces. They simply bounce off one another in these elastic collisions. They move very quickly, and they're in constant random motion. Finally, our characteristics. We can think of our gases as compressible, so we can fit a large amount into a small space and kind of fill up that 99% empty space that we were talking about in its container. They have an indefinite shape and an indefinite volume. Another vocab word that we might hear along with our gases is diffusion. So when we refer to diffusion, we're referring to the movement of molecules from areas of a high concentration to areas of a lower concentration. And finally, this word looks really similar to diffusion, but it is going to be slightly different. If we refer to effusion, we're still talking about gases traveling. And effusion is the process that occurs when a gas escapes through a small hole in the container. This is going to depend on the mass of the molecules. So for example, down here, we can look at helium escaping through a small hole through its container, And if you notice, a lot of helium molecules have been able to fit through this pinhole. If we look at a larger molecule, such as ethylene oxide over here, these are larger molecules, so not as many have been able to effuse through this pinhole. So fusion really is just going to depend on the mass of the molecules. Whereas diffusion won't really matter what the mass of those molecules are because they don't have to fit through this small pinhole here. There is a way to calculate our rate of diffusion. We're not going to focus on that in this course, but it is something that can be done. And maybe if you take second year chem, that is something that you would say. Like we said, since helium was a smaller molecule, it was able to effuse faster. So since it was lighter, helium was able to travel faster than ethylene oxide.